Welcome to Lecture 13. This is a fairly straightforward lecture on the calculation of the mean and variance of a distribution. And we will learn in this lecture how to calculate the mean and variance for both a discrete random variable and for continuous random variables. And let's start with a problem. So we'll say problem 24.6.2, find the mean and variance of x, the random variable x, where x is equal to the number a fair die turns up. Now, first of all, let's make the note that this random variable x is a discrete random variable. In other words, the values that x can assume are discrete values. They do not fall in a continuous range of values. The only values that x can assume for a fair die are 1, 2, 3, 4, 5, and 6. Now, for a discrete random variable, the mean, which is designated mu for both discrete and continuous random variables, but the way that it is defined for a discrete random variable is the sum over j of f of x sub j times x sub j. And this is over all the possible values that the random variable can assume. These little x sub j's, they are the different values that the random variable x can assume. And little f of x sub j, remember, little f is the probability. When we're talking about discrete random variables, this is called the probability function, and it is the f of little x sub j is the probability that the random variable has the value x sub j. So we just take each value that the random variable can assume and multiply it by the probability that the random variable does assume that value. And we do that for each of those values and then add it all up, and that is the mean. So let's do that for this case. Now, as we've already noted, the values that this random variable can assume are 1, 2, 3, 4, 5, and 6. So we have f of 1 times 1 plus f of 2 times 2 plus f of 3 times 3 plus f of 4 times 4 plus f of 5 times 5 plus f of 6 times 6. Now, the fact that this is a fair die will enter into the calculation right here at the next step. The fact that it is fair means that all of these probabilities are the same. If it was an unfair die, as long as we knew what the values of the different f's were, the different probabilities of it landing on its different or displaying its different faces up, as long as we knew those probabilities, we could still calculate the mean. But it's just that the only difference would be that then the different f's would have different values. But since this is a fair die, all 6 values are equally likely and equal to 1/6. So therefore, we have 1/6 times 1 plus 1/6 times 2 plus 1/6 times 3 plus 1/6 times 4 plus 1/6 times 5 plus 1/6 times 6. And therefore, let's see, I guess we'll have 1 plus 2 plus 3 plus 4 plus 5 plus 6 over 6. And this will be 6 and 4 is 10 and 11. So we have 21 over 6. So mu will be 3.5 for this random variable. That is the mean value of that random variable. And that's all there is to calculating the mean of a discrete random variable. Just again, you have to identify all the values that it can assume, multiply each by the probability that the random variable does assume that value, and then add all those up, and you get your answer. Now for the variance of a discrete random variable, so let's say to calculate the variance of a discrete random variable, well, first of all, variance, the symbol for variance is sigma squared. And again, just as mu is the symbol for mean for both discrete and continuous random variables, so is sigma squared the symbol for the variance for both discrete and continuous random variables. But the way that it's calculated for a discrete random variable is the following. Again, we want to sum over all of the values that the random variable can assume, and the what we're going to sum is xj minus mu squared times the probability of xj. So for each value that the random variable can assume, we're going to subtract mu from that value, square what we obtain, and then multiply by the probability that the random variable assumes that value. And we're going to do that for all of the values and add them all up. So in this case, let's see what we would get. And notice, by the way, that in order to calculate the variance, you need to calculate mu first, because mu is part of this formula for sigma squared. So let's make sure we understand how to apply this formula. So sigma squared, again, we're going to sum over all the values that the random variable can assume. So we will have 1 minus 3.5 squared times f of 1 plus 2 minus 3.5 squared times f of 2 plus 3 minus 3.5 squared times f of 3 plus 4 minus 3.5 squared times f of 4 plus 5 minus 3.5 squared times f of 5 plus 6 minus 3.5 squared times f of 6. And again, since this is a fair die, f of 1, f of 2, f of 3, f of 4, f of 5, and f of 6 are all equal to 1/6, and therefore sigma squared will be 1 minus 3.5 squared plus 2 minus 3.5 squared plus 3 minus 3.5 squared plus 4 minus 3.5 squared plus 5 minus 3.5 squared plus 6 minus 3.5 squared, all divided by 6. And let me calculate this now. And by the way, the reason in these lectures that I try to concentrate on doing even-numbered problems, we might have done a few odd-numbered ones, but in general I try to do the even-numbered ones so that you can have the odd-numbered ones for practice, because of course the answers to most of the odd-numbered problems are at the back of your text. So just to remind you, as I said before, probability is a topic where it's particularly helpful to get lots of practice, and I hope that you are practicing on this topic, because it can be, I think as you've already seen, it can be sort of tricky. So let's stop for just a moment to make this calculation and then finish this problem. Okay, so unless I've made an error, when we sum up those terms in the numerator, we get 17.5, and therefore the variance is 17.5 divided by 6, or 2.916 repeating. And that's how we would calculate the variance of a discrete random variable. So as I mentioned from the beginning, this is a pretty straightforward process, just a matter of understanding how to apply the formulas. Again, here's the formula for the variance, and here is the formula up here for the mean. So now let's look at another problem, this time one with a continuous random variable. And for this case, let's look at problem 6. So we have 24.6.6, and it says f of x, well, actually, find the mean and variance if f of x is equal to k times 1 minus x squared if negative 1 is less than or equal to x is less than or equal to 1 and 0 otherwise. Okay, so the this refers to a continuous random variable. Because the random variable here can assume any value between -1 and 1, but no value outside of that. And so it can assume values in a continuous range, and therefore this is a continuous random variable. Now, for the mean of a continuous random variable, remember what we did for the mean of a discrete random variable was we added up all the values it could have multiplied by the respective probabilities that the random variable did indeed have that particular value. Well, here it's a very similar kind of thing, except for instead of adding up, we integrate. So here we would integrate from -1 to 1 of little f of x times x dx. Same, very similar to what we had before, except the summation now becomes an integral. But you notice that we cannot continue with this calculation at this point because f of x has this value k in it, and so therefore we can't calculate mu unless we know k. So the first thing we're going to have to do is, let's say, first find k. And I hope that you all will remember how to do that. To find k, we use the fact that the integral, if we integrate f of x dx from -infinity to infinity, we will get 1, because that represents the probability that the random variable has some value between -infinity and infinity, so that's 1. Now, since little f of x is equal to 0 everywhere except between -1 and 1, this integral can be written like this: integral -1 to 1, and then in that range is equal to k times 1 minus x squared. And so the integral can be written in this form, and therefore if we take k out of the integral, we'll get k times and well, let's go ahead, well, I guess -1 to 1, 1 minus x squared dx is equal to 1, and therefore we have k times x minus x cubed over 3, evaluated from -1 to 1, is equal to 1, and therefore we get k. And when we evaluate this at the upper limit, we're going to get 1 minus 1 over 3, so 2/3. And then when we evaluate this at the lower limit, we're going to get -1 for x, and then minus, okay, we'll have x cubed, so minus a -1 over 3. And that's equal to 1. Well, let's think about this. This is -1 minus a -1/3, so that's -1 plus 1/3, or -2/3. So we have 2/3 minus a -2/3, which is the same thing as 2/3 plus 2/3, or 4/3. So k times 4/3 is equal to 1, and therefore k is equal to 3/4. So this is the k that we need for this density function, and now we can take that and plug it back in up here in our calculation, and we're ready now to find the mean value of this random variable. So we get mu is equal to the integral from -1 to 1, and f of x is now in that range from -1 to 1. It's equal to k, which is 3/4, times 1 minus x squared. 1 minus x squared. And then we have this x and dx. The 3/4 can be pulled out of the integral, and we have 3/4, the integral from -1 to 1 of x multiplying through by multiplying 1 minus x squared by x, we get x minus x cubed dx. Now, if you are very, very alert, you'll already see that the value of this integral is 0. And the way that you can see that is that this is an odd function. By an odd function, a function is said to be odd. A function, let's say g of x, is said to be odd if g of negative x is equal to negative g of x. So, for instance, the sine function, since sine of negative x is negative sine of x, the sine function is an odd function. The cosine function, on the other hand, is an even function, because cosine of negative x is the same thing as cosine of positive x. So cosine is an even function, sine is an odd function. And when you integrate an odd function over symmetric limits, symmetric about 0, which these limits are, when you integrate an odd function over symmetric limits, you'll always get 0. Just like, for instance, if you integrate sine x from negative pi over 2 to pi over 2, or from negative pi over 10 to pi over 10, or negative 100 pi to 100 pi, whatever, as long as you integrate an odd function over symmetric limits, you'll always get 0. And we're going to get 0 here too. But if you don't notice that, that's fine. Just go ahead and proceed with the integration. So you get mu is equal to 3/4. And then you'll have, when you integrate x, you'll get x squared over 2. And when you integrate x cubed, you'll get x to the 4th over 4. And we're going to evaluate that from -1 to 1. And so this will give us 3/4. And then when we evaluate at the upper limit of 1, we will get 1/2 minus 1/4. So that will give us 1/4. And then when we evaluate at the lower limit of -1, we get -1 squared. That's 1/2 minus -1 to the 4th is 1/4. So 1/2 minus 1/4 is 1/4. And as predicted, indeed, we will get 0. So that's how we calculate the mean of a continuous random variable. And now let's calculate the variance. And again, the calculation, just like the calculation of the mean of a continuous random variable, is very similar to the calculation of the mean of a discrete random variable. You just replace summation by integration. So the same is true for calculating the variance. So we get integral from -infinity to infinity of x minus mu squared f of x dx. And so now in this case, that will become, since f of x, remember, f of x is equal to 0 everywhere except in the range from -1 to 1. So therefore this can become integral -1 to 1. And the x minus mu part, since mu is equal to 0, that's just x. And then we square it. So we have x squared. And then for f of x, in that range between -1 and 1, f of x is, remember we found k is equal to 3/4, so 3/4 of 1 minus x squared. So we'll have 3/4 and then 1 minus x squared dx. And so the 3/4 can come out, and we have the integral from -1 to 1 of x squared minus x to the 4th dx. And now this function is an even function, and if you recognize that, you can maybe make this integration just a little bit quicker. When you integrate an odd function over symmetric limits, we said you always get 0. When you integrate an even function over symmetric limits, what you get is twice the value. I'll put this to the side, but I won't pursue it because I don't expect you to readily see things like this. I'm just pointing it out to you. So since this is an even function, this integral would be equal to twice the integral from 0 to 1 of x squared minus x to the 4th dx. And I'll let you pursue that line of reasoning if you wish, and you can check. But again, as I said, I don't expect you to see things like that very quickly, and so don't worry about it if you didn't. We'll just proceed over here at the left. We'll proceed with integration in the normal way. So we will get 3/4, and then when we integrate x squared, we'll get x cubed over 3. And when we integrate x to the 4th, we get x to the 5th over 5. And that's from -1 to 1. And therefore, sigma squared is going to be 3/4 times, at the upper limit of 1, we get 1/3 minus 1/5. And let's see, I guess that will be 5/15 minus 3/15. So that's the same thing as 2/15. And then at the lower limit, so we're going to subtract off what we get at the lower limit. And at the lower limit, we will get a minus 1/3 minus a negative 1/5, which is the same thing as negative 1/3 plus a positive 1/5. And so that will give us a negative 2/15. Negative 2/15 here. And so we have 3/4 times 4 over 15, and the 4's cancel, and we get 3 over 15, or 1/5. So sigma squared, the variance for this continuous random variable, is 1/5. And that concludes the discussion of how we find the mean and the variance of a continuous random variable. And that's all there is to this lecture. So now let's look at some problems related to this lecture. Actually, before proceeding to the problems for this lecture, I would like to talk about the problems from lecture 12. Okay, so here are the problems from lecture 12, and these, well, what I'm about to say is relevant to these problems and is also relevant to the quiz for lecture 12. So pay attention, because what I'm about to say could be useful. It could help you to save some time on some problems. So the situation, again, just to refresh your memory, is that x, which is measured in millimeters, is the thickness of washers, and x has the density f of x equals kx if 0.9 is less than x is less than 1.1 and 0 otherwise. And problem 12-1 asks for K, and then problem 12-2 asks for the probability that a washer will have a thickness between 0.95 millimeters and 1.05 millimeters. And you could use, probably the way that most of you pursued this problem was to, or proceeded with it, I should say, is that you solve for K first in 12-1 and then use that in B12-2 to find the desired probability. But I want to show you how to solve B12-2 without first finding K. And this is a useful thing to know, and again, as I said, it is something that could have been used in the quiz 12. Okay, so the probability that we want, again here, the probability is that X will be between 0.95 and 1.05. And so P is equal to, we know that's the integral from 0.95 to 1.05 of f of little x dx. And again, f of x, I'll just repeat for you that f of x in this problem is equal to kx if 0.9 is less than x is less than 1.1, and it's equal to 0 otherwise. And of course, it looks like our difficulty here is that we have that unknown value K. Like I say, you have to assume now that we haven't done problem B12-1. We're just trying to solve B12-2 directly without first finding K. So how are we going to do this? If f of x has K in it, and we need to integrate f of x in order to find P, then how are we going to solve this problem? Okay, well, let's make another observation. We know that if we integrate from 0.9 to 1.1, now this is the entire range over which f of x is non-zero. So if we integrate f of x over that complete range, we're going to get 1. Now, let's divide this top equation by the second equation, and what we will get is P over 1 is equal to the integral from 0.95 to 1.05 of f of x dx divided by the integral from 0.9 to 1.1 of f of x dx. And of course, P divided by 1 is simply P. And so we have P is equal to integral from 0.95 to 1.05 of f of x dx divided by the integral from 0.9 to 1.1 of f of x dx. And now if we substitute in the expressions for f of x, remember f of x is just kx, so we have integral 0.95 to 1.05 of kx dx divided by integral from 0.9 to 1.1 of kx dx. And remember that k is a constant, so it could be pulled out of both integrals. And then we have that the fact that k, we have a k in the top and in the bottom, so it will cancel. And so we're just left with integral 0.95 to 1.05 of x dx over integral 0.9 to 1.1 of x dx. And of course, these, now there's no longer any k in this problem, and therefore you can proceed. And this is how you would come up with the answer, how you could arrive at the answer for problem B12-2 without ever finding k. And so this is a useful thing to know about. It is also something that you could have done in quiz 12. And before we leave this topic, let me just say that if you look at this equation here, saying that p is the integral of f of x dx over this range divided by the integral of f of x dx over this range, it really makes perfectly good sense. Let me explain what I mean. So if we think about the f of x that we have for this problem, so here's x, and here is f of x, and remember the f of x is equal to kx when x is between 0.9 and 1.1. So I can say that somewhere this will be 0.9 and this will be 1.1, and so we're going to have something like this. It really doesn't matter the exact shape of f of x for the argument that I'm going to make, but if we want it to be precise, then f of x looks something like this. It's a linear function of x between 0.9 and 1.1. And so we can extend like that. That's what f of x is equal to. It's equal to 0 everywhere else, but it's equal to kx between 0.9 and 1.1, and at the moment we don't know what k is equal to. We know that the integral of f of x dx from 0.9 to 1.1, this integral, as we said already, that integral, which is the area enclosed here, this integral, the area is equal to 1, but if we really wanted to find out what that implies the value of k is, we have to do some work. But notice that the p that we want, well, this could be regarded as the area under the f of x curve from 0.95 to 1.05. So we have this area right here is p. And so what this equation right here tells us is that the probability is simply the ratio of this area to the entire area. And once we know that, then we don't have to calculate k at all. And it makes perfectly good sense at all. The probability that x will be somewhere in here is simply the ratio of this area to the ratio of the entire area, because x has to fall somewhere within the entire area. So I think that this makes perfectly good sense, and it's a handy thing to know about. For instance, as we just saw, it would save you just a little bit of time. You don't have to find k first. Not that that would be a great deal more work, but it would save you a little bit of time. So this is a handy thing to know about. So that concludes our remarks about the problems from from lecture 12, and now the problems for the present lecture, for lecture 13. Okay, so the problems for lecture 13 are the following. The first one, B13-1, which is, I guess, actually identical to problem 24.6.13 in your text. It says, what is the expected daily profit if a store sells X air conditioners per day with probability little f of 10 equals 0.1, little f of 11 equals 0.3, little f of 12 equals 0.4, and little f of 13 equals 0.2, and the profit per conditioner is $55. And the choices are A, $643.50, B, $11.70, C, $55, and D, $2,530. And then for problem B, 13-2, which is very similar to but not quite identical to problem 24.6.15 in your text, says a small filling station is supplied with gasoline every Saturday afternoon. Assume that its volume X of sales in ten thousands of gallons has the probability density little f of x equals 6x times 1 minus x if 0 is less than or equal to x is less than or equal to 1 and 0 otherwise. Determine the mean. And the choices are A, 1, B, 1/4, C, 3/4, and D, 1/2. And then, as usual, there will be other problems in class. So that concludes lecture B13, and good luck.